We are about to find alien life. Not in 100 years, not in 50, in our lifetime, possibly within the next few decades. And the place it's going to happen is not where most people think. It's not Mars. Mars is dry, irradiated, and probably dead. It's not some distant exoplanet, thousands of light years away. It's right here in our solar system orbiting Saturn. A tiny moon smaller than the state of Colorado that is actively spraying its own ocean into space at 300 liters per second. And that ocean contains organic molecules, hydrothermal vents, phosphorus, hydrogen, carbon, and almost every single ingredient that life on Earth needed to get started. Its name is Enceladus, and in October 2025, scientists reanalyzed data from the Cassini spacecraft and found new organic molecules that had never been seen there before. Molecules that on Earth are part of the chemical chains that lead directly to life. 5 months later, the European Space Agency officially confirmed that landing on this moon is now their #1 scientific priority for the next 50 years. They're building a spacecraft right now. So let's go through everything. How we found out about this place, what's inside it, what we found in 2025, why this moon beats every other candidate for alien life in the solar system, what it would take to actually go there, and what finding life there would mean for every human being on this planet. This is the full story of Enceladus. To understand why Enceladus is special, you first need to understand the old way people thought about the search for life in our solar system. For decades, the strategy was simple: follow the sun. Life needs liquid water. Liquid water needs heat. Heat comes from the sun, so you look for planets close enough to the sun that water stays liquid. This region is called the habitable zone, or sometimes the Goldilocks zone. And in our solar system, Earth sits comfortably in the middle of it. Venus is too hot, Mars is too cold. Earth is just right. Under this framework, the outer solar system was written off. Jupiter, Saturn, Uranus, Neptune. These planets are between 400 million and 3 billion miles from the Sun. At those distances, temperatures in space drop to -200 Celsius and below. Water doesn't stay liquid out there. It freezes solid, so nothing could live out there. Case closed. That was the conventional wisdom for most of the 20th century. And then, in 1977, something happened that completely upended it. Scientists were exploring the deep ocean floor near the Galapagos Ridge in the Pacific, and they found something nobody expected. Hydrothermal vents, cracks in the seafloor where superheated chemical-rich water gushes up from the Earth's interior. And living around those vents, in water with temperatures up to 400 degrees Celsius, under crushing pressure, in complete darkness, far below any sunlight, was an entire ecosystem. Worms, clams, shrimp, bacteria, a whole web of life built not on photosynthesis, not on sunlight, but on chemosynthesis, the ability to extract energy from chemical reactions. This single discovery shattered the assumption that life requires sunlight. If life can thrive at the bottom of Earth's ocean, in total darkness, sustained by chemical energy from the rocks below, then the rules changed. You no longer needed to be in the habitable zone. You just needed liquid water and a source of chemical energy. And that suddenly made the icy moons of the outer solar system a lot more interesting. Because here's the thing, those moons are not frozen solid all the way through. Some of them are being squeezed and stretched by the enormous gravity of the gas giants they orbit. That squeezing and stretching, called tidal heating, generates friction. Friction generates heat, and heat melts ice from the inside. Beneath the frozen surface of certain moons, liquid water oceans have been sitting for billions of years in complete darkness, potentially in contact with rocky seafloors, potentially with hydrothermal vents, potentially harbouring life. Let's spend a moment on tidal heating, because it's one of the most important physical processes in this whole story, and most people have never really thought about it. You know how the moon causes tides on Earth. The moon's gravity pulls on our oceans, creating bulges of water on the side facing the moon and the side facing away. As Earth rotates, those bulges move around the planet. That motion dissipates energy as heat, actually a tiny amount, but over billions of years it has gradually slowed Earth's rotation and moved the moon slightly farther away. Now imagine you're a small moon orbiting a planet as massive as Saturn. Saturn is 95 times more massive than Earth. Its gravitational pull is enormous. And if your orbit around Saturn is not perfectly circular, if it's even slightly elliptical, then Saturn's gravity pulls on you with varying strength depending on where you are in your orbit. When you're closer, the pull is stronger. When you're farther, it's weaker. Your whole body gets squeezed and stretched in a rhythmic cycle over and over, millions of times over billions of years. That squeezing and stretching is not gentle. It generates heat inside the moon, the same way a metal paperclip gets warm when you bend it back and forth repeatedly. The material flexes, molecules rub against each other, and thermal energy is released. For a small moon with a rocky interior surrounded by ice, this process can melt the ice from the inside and maintain a liquid ocean indefinitely. Enceladus's orbit around Saturn is slightly elliptical, partly because of gravitational interactions with another of Saturn's moons called Dione. Models suggest that resonant perturbations from Dione could provide the necessary periodic eccentricity changes to maintain the subsurface ocean of Enceladus. This gravitational dance, Saturn pulling on Enceladus, Dione nudging its orbit, has been keeping Enceladus warm for potentially billions of years. This is a completely different energy source from the Sun. It's gravitational energy being converted to thermal energy through tidal flexing. It works at any distance from any star. It works in complete darkness. It works in the outer solar system, the inner solar system, around red dwarfs, around gas giants. Wherever you have a moon in a non-circular orbit around a massive planet, the implications for the search for life are staggering. The traditional habitable zone is one narrow band around a star, but tidally heated ocean worlds can exist at virtually any distance from their star in any planetary system. This potentially multiplies the number of habitable environments in the galaxy by an enormous factor. And Enceladus is the proof of concept. Of all the ocean worlds in the outer solar system, Europa, Titan, Ganymede, Callisto, possibly even Pluto, Enceladus is now considered the single best candidate for life. And the reason for that comes down to one incredible accident of discovery that happened in 2005. But first, let's talk about what we knew before 2005, because Enceladus was not exactly on anyone's radar as a top priority for the search for life. The moon was first observed in detail by the Voyager spacecraft in the early 1980s. Voyager 1 and Voyager 2 flew through the Saturn system and sent back images of Enceladus that immediately stood out as strange. The surface was bright, almost impossibly bright. Enceladus is the most reflective body in the entire solar system. It reflects about 99% of the sunlight that hits it, Compare that to Earth's moon, which reflects only about 12% of sunlight, or to fresh snow on Earth, which reflects about 80–90%. Enceladus is brighter than fresh snow. That brightness was a clue, though scientists weren't sure what it meant. Bright usually means fresh ice. Surfaces that have been sitting for billions of years get darker over time as they collect dust, micrometeorites and organic residue. A very bright surface means the ice is being renewed somehow. Something was resurfacing Enceladus, but Voyager couldn't tell what. Voyager also noticed that Saturn's E-ring, a faint, diffuse ring that's much broader and thinner than the famous main rings, had its densest part right at the orbit of Enceladus. That was another unexplained clue. Something at Enceladus's orbit was feeding material into that ring. But what? These mysteries sat largely unanswered for more than 2 decades, until Cassini arrived. The Cassini-Huygens mission was one of the most ambitious space exploration projects in history. It was a joint project of NASA, the European Space Agency, and the Italian Space Agency. It launched in 1997 and took 7 years to reach Saturn, finally arriving in 2004. The spacecraft included an orbiter, Cassini, that would study Saturn and its moons for over a decade, and a probe, Huygens, designed to descend through the atmosphere of Saturn's largest moon, Titan, and land on its surface. Cassini was equipped with 12 scientific instruments covering an extraordinary range of capabilities: visual and infrared cameras, a radar system, a magnetometer, an ultraviolet imaging spectrograph, a radio and plasma wave science instrument, and critically, a cosmic dust analyzer, an instrument designed to directly study the composition of dust and ice particles in Saturn's environment by measuring what happens when they impact a metal target at high speed. Nobody built Cassini specifically to look for life at Enceladus. The mission was designed to study the Saturn system broadly. Enceladus was on the list of moons to observe, but it was not the headline target. Titan got most of the early attention because Titan has a thick nitrogen atmosphere, lakes of liquid methane, and fascinating organic chemistry. Titan still has enormous scientific value, but Enceladus stole the show. In 2005, Cassini's cameras obtained the first ever detailed images of the south polar region of Enceladus, revealing a surprisingly youthful and complex terrain almost entirely free of impact craters. The surface was littered with house-sized ice boulders. Tectonic patterns, unlike anything seen elsewhere in the solar system, crisscrossed the landscape. And then the scientists looked more carefully, and they saw something that made them physically stop and reread the data, its gazers. Enormous plumes of water vapor and ice particles erupting from cracks in the south polar surface, shooting hundreds of kilometers into space. The jets contain water vapor moving at up to 2,189 kilometers per hour, pushing 250 kilograms of water vapor into space every second. Enceladus, a moon with a surface temperature of minus 200 degrees Celsius, was actively venting its internal ocean into space, not slowly, not occasionally. Continuously, year after year, decade after decade, the reaction at mission control was immediate and electric. Scientists started redesigning Cassini's flight plan on the fly. The original mission profile had Cassini making relatively distant flybys of Enceladus. Once the plumes were discovered, the team started pushing for closer and closer passes. Eventually, they convinced NASA to approve flybys that took Cassini within 50 kilometers of Enceladus' surface, essentially skimming the top of the plumes. and the Cassini spacecraft was right there, with instruments designed to analyse exactly this kind of material. What came next was one of the most consequential series of scientific discoveries in the history of planetary exploration. The cracks the jets were coming from were quickly nicknamed the Tiger Stripes. The Tiger Stripes are 4 prominent fractures, each approximately 84 miles, 135 kilometres long, that cross the Moon's south polar terrain. They glow in infrared because they're warmer than the surrounding ice. They're actively deforming, opening and closing slightly as Enceladus orbits Saturn and the tidal forces change, and they go deep, all the way down through the ice shell to the liquid ocean below. The Tiger Stripes are one of the most geologically remarkable features in the solar system. Each one is a canyon-like fracture bounded by ridges of ice pushed up on either side, running in nearly parallel lines across the South Pole. The spacing between adjacent Tiger Stripes is surprisingly regular, about 35 kilometers apart. This regular spacing is not a coincidence. It's the result of a specific physical process where the opening of one crack changes the stress distribution in the surrounding ice in a way that makes the next crack form at a predictable distance. The Tiger Stripe fissures remain open because liquid water within them is sloshed around by tidal forces produced by Saturn's gravity, releasing energy as heat. That stops the crack from freezing shut. At the same time, water vented from the crack falls back as ice, building up the edges of the fissure and weighing it down, just enough to set off a parallel crack about 20 miles away. So the Tiger Stripes are self-maintaining. The process of erupting water keeps the cracks from freezing. The ice build-up at the edges triggers new cracks at regular intervals. The whole system has been in a dynamic equilibrium, possibly for millions of years. Think about what this means. Enceladus is not just an ocean world with ice on top and water underneath. Enceladus has a direct physical pipe connecting its ocean to space. There are no miles of solid ice to drill through. You don't need a cryobot that slowly melts its way down to the ocean floor over years. The ocean is already coming to you. It's already in space. You can fly through it. The plume releases water vapor at a rate of about 300 litres per second, enough to fill an Olympic-sized swimming pool in just a couple of hours. This is genuinely extraordinary. No other ocean world in the solar system, not Europa with its potentially habitable ocean, not Titan with its methane lakes, not Ganymede with its vast deep ocean, does this. Enceladus is uniquely, generously, almost invitingly open. It's handing us its ocean chemistry on a plate. One more thing about the plumes that's worth appreciating. The intensity of the eruption varies significantly as a function of where Enceladus is in its orbit around Saturn. The plumes are about 4 times brighter when Enceladus is at the point in its orbit most distant from Saturn than when it is closest. This variation is exactly what you'd expect from tidal forcing. When Enceladus is farther from Saturn, the tidal stretching pulls the Tiger Stripe fissures open slightly. When it's closer, the tidal compression squeezes them shut. The ocean literally breathes in and out with each orbit. That orbital period is about 32.9 hours, so the plumes pulse on a 33-hour cycle driven by Saturn's gravity, that kind of dynamic. Responsive system is exactly what you'd expect from a moon, with a liquid ocean that's intimately connected to its surface geology through open cracks. It's another piece of evidence that the model, ocean, through cracks, plumes, is correct. But let's get into what's actually in those plumes, because the contents are where this story gets truly remarkable. When Cassini first detected the plumes in 2005, it found water vapour, good, consistent with a liquid water ocean. Then, over the following years, as the mission continued and instruments were aimed at Enceladus again and again, the list of detected compounds grew and grew and grew. Water salt, silica nanoparticles, tiny grains of rock that form only when hot water interacts with rock at high temperatures, molecular hydrogen, carbon dioxide, methane, simple organic molecules, more complex organic molecules, and in 2023, the one compound that, in the scientific community, generated the loudest collective gasp, phosphate. Cassini's cosmic dust analyzer detected sodium phosphates in ice grains emitted from Enceladus, suggesting phosphorus is readily available in the Moon's ocean in the form of orthophosphates, with concentrations at least 100 times higher than in Earth's oceans. 100 times higher than Earth's oceans. The phosphorus concentration in Enceladus's plumes is 100 times richer than what we swim in at the beach. Why does this matter? Because phosphorus is one of the 6 elements that life on Earth absolutely requires. The famous acronym is CH-NOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These 6 elements make up the overwhelming majority of all biological molecules. DNA, RNA, proteins. Cell membranes, everything life builds itself from, is made primarily of these 6 things. Before the phosphate discovery, Cassini had already found carbon, hydrogen, nitrogen, and oxygen in Enceladus's plumes. But the question of phosphorus had been hanging open. Some models suggested Enceladus's ocean chemistry might sequester phosphorus in minerals on the seafloor, locking it away from solution where life couldn't use it. Those models were wrong. The recent identification of phosphates in the plume means that 5 of the 6 bioessential CH-NOPS elements have been detected in material from Enceladus. 5 out of 6, the only one still not confirmed is sulfur, and most scientists expect it's there too, just waiting for a more sensitive instrument to find it. Let's put this in perspective. In 2005, we knew Enceladus had water and geysers. In 2014, we confirmed a global ocean. In 2017, we found hydrothermal vents producing molecular hydrogen. In 2018, we found large organic molecules. In 2023, we found phosphorus. And then in October 2025 came the latest and, in some ways, most exciting chapter. A new analysis of archival data from the Cassini spacecraft confirmed that the icy jets shooting from Saturn's moon, Enceladus, contain organic molecules, the key building blocks of life. The research team established the oceanic origin of these molecules by confirming that certain organics found in Saturn's ring were also abundant within fresh ice samples, and identified entirely new molecules never before documented in Enceladus's plumes. This distinction, oceanic origin, is absolutely critical. Before this study, a competing hypothesis had been gaining traction. Maybe the organic molecules in Enceladus's plumes weren't coming from the ocean at all. Maybe they were being produced right on the surface by radiation from Saturn's magnetosphere bombarding the ice. If that were true, the plume chemistry would tell us nothing about what's inside the ocean. It would just be surface radiation chemistry with no implications for habitability. The 2025 study killed that alternative. By comparing the chemistry of fresh ice grains collected by Cassini during an actual close flyby, material that was inside the moon just minutes before the spacecraft flew through it. With older grains that had been drifting in Saturn's E ring for days or weeks being bombarded by radiation, the team could distinguish between the two. The fresh, unprocessed material had the same organic compounds as the processed E ring material. The organics were already there, in the fresh ice straight from the ocean. They weren't made on the surface by radiation. These molecules we found in the freshly ejected material prove that the complex organic molecules Cassini detected in Saturn's E ring are not just a product of long exposure to space, but are readily available in Enceladus's ocean, said Frank Postberg, a co-author of the study. And then came the list of new molecules. This is where it gets chemically exciting. The newly detected molecular fragments included aliphatic and heterocyclic esters and alkenes, ethers, ethyl compounds, and nitrogen on Earth, these same molecules are involved in the chains of chemical reactions that ultimately lead to the more complex molecules essential for life. Let me translate that out of chemistry into plain language. Aliphatic compounds are the carbon chain backbones of organic chemistry. Think of them as molecular scaffolding, long chains of carbon atoms with hydrogen attached, forming the skeleton of fatty acids, lipids, and many other biologically important molecules. Heterocyclic compounds are ring-shaped molecules where some of the atoms in the ring are not carbon, for example nitrogen or oxygen. These ring structures are central to biology. The bases that make up DNA and RNA, adenine, guanine, cytosine, thymine, uracil, are all heterocyclic compounds, so are many vitamins and enzyme cofactors. Esters are compounds formed when acids and alcohols react, and on Earth, esters appear everywhere in biology. The bonds that hold fatty acids together in cell membranes are ester bonds. Many signaling molecules are esters. Alkenes contain carbon-carbon double bonds, which make them chemically reactive and important intermediates in organic synthesis. Ethers appear in everything from anesthetics to the sugar backbone of DNA itself. None of these are life itself. But on Earth, you find these exact classes of molecules in the environments where life either exists or is being assembled from scratch. They're the intermediate steps, the building blocks of the building blocks. They are the chemical language that life speaks, translated into simpler words. Having clear evidence of a variety of organic compounds from inside an extraterrestrial water world is incredible and further strengthens Enceladus' potential for habitability. It appears that Enceladus has all the ingredients for life as we know it, said lead author Nozer Khawaja. All the ingredients. That's not a minor claim. That's a scientist saying, everything we know that life needs, we've now found it there. Now, let's talk about the hydrothermal vents, because they are possibly the most important single feature of Enceladus from an astrobiological standpoint. The discovery of vents on Earth in 1977 was revolutionary, but the deeper implication took years to fully sink in. Before that discovery, the assumption was that life on Earth is fundamentally solar-powered. Sun hits plants, plants feed animals, animals feed other animals. Everything traces back to photosynthesis. Remove the sun and life dies, but the vent ecosystems work on completely different principles. The vents release hydrogen sulfide and other reduced chemicals from the hot rock below. Certain bacteria can oxidize these chemicals, react them with oxygen or sulfate from the seawater, and extract energy from that reaction. This is chemosynthesis. These bacteria are the foundation of the vent food web. Everything else at the vent, the tube worms up to 2 meters long, the crabs, the mussels, the shrimp. Ultimately depends on these chemosynthetic bacteria. No sunlight required, not even a little bit. The entire ecosystem runs on chemical energy from the Earth's interior. And here's the really striking connection to the origin of life. Some of the leading theories for how life first began on Earth invoke hydrothermal vents as the birthplace. Not the hot, black smoke vents where sulfides shoot out at 400 degrees, but a different type. Alkaline, cooler vents like the Lost City hydrothermal field in the Atlantic Ocean. These vents produce molecular hydrogen by a process called serpentinization, where seawater reacts with certain types of rock called ultramafic rocks, producing hydrogen gas and releasing heat. The hydrogen provides chemical energy. The alkaline, warm conditions create natural chemical gradients that some researchers believe drove the first self-replicating chemical systems into existence. The Lost City hydrothermal field was discovered in 2000, and it immediately became a landmark site for origin of life research. It sits at a mid-ocean ridge in the North Atlantic, about 800 meters below the surface. Its chimneys, which can reach 60 meters in height, making them the tallest hydrothermal structures ever found, are made of white carbonate and serpentinite minerals rather than the black iron sulfides of typical smoke vents. The water coming out is warm but not scalding, around 40 to 90 degrees Celsius. The pH is highly alkaline, around 9 to 11, and the fluid is rich in hydrogen and methane. The key thing about alkaline hydrothermal vents for origin of life is the chemical gradient. The hot, alkaline, hydrogen-rich fluid from the vent meets the cooler, slightly acidic, carbon dioxide-rich ocean water. This gradient, a difference in pH and chemistry across a thin boundary, can drive chemical reactions spontaneously. Some researchers, most notably Nick Lane and Mike Russell, have argued that the thin mineral walls of hydrothermal vent structures acted as natural proton gradients, essentially the same mechanism that all cells on Earth use today to generate energy from their membranes. In this view, life didn't invent the proton gradient, it inherited it from the vent. Now look at what Cassini found in Enceladus's plumes. Cassini found molecular hydrogen in Enceladus's plume, consistent with water circulating through the seafloor, where it is heated and interacts chemically with rock, creating chimney-like vents. With the discovery of hydrogen gas, scientists concluded that there is a source of chemical free energy in Enceladus ocean, molecular hydrogen, produced by serpentinization, the exact same chemical signature that marks alkaline hydrothermal vents on Earth, the very vents that some scientists believe were the cradle of life. Evidence suggests hydrothermal reactions in Enceladus's interior involve temperatures greater than 90 degrees Celsius, with moderate salinity and an alkaline pH between 8.5 and 10.5, alkaline warm hydrothermal, chemically active at the water-rock interface. These are the exact words that researchers use to describe the Lost City hydrothermal field on Earth, the closest analogue we have to the proposed birthplace of terrestrial life. If you wanted to design a place in the solar system that recreates the conditions thought to have produced life on Earth, you would design something very close to what Cassini found inside Enceladus. The silica nanoparticles that Cassini found are another critical piece of this picture. Silica, silicon dioxide, forms specific nanoscale particles only when water at temperatures above 90 degrees Celsius reacts with silicate rock. The size of the particles tells you the temperature and salinity of the water they formed in. The silica nanoparticles in Enceladus's plumes pointed to hot water, well above 90 degrees, reacting with rock. Then that water being transported up through the ice shell and into the plume. This is not ambient chemistry. This is active, hot, mineral-laden water gushing from a rocky seafloor. This is geology. This is the same kind of process that drives hydrothermal systems on Earth. The combination of molecular hydrogen and silica nanoparticles was, for many scientists, the moment Enceladus stopped being an interesting moon and became the most compelling astrobiology target in the solar system. Now, there's something important to understand about what we mean when we say life as we know it. The phrase gets thrown around a lot, but it has a specific meaning. Life on Earth uses water as its solvent, carbon-based chemistry for its molecular machinery, and specific energy sources to drive its metabolism. When we search for life using these criteria, we're being deliberately conservative, limiting ourselves to what we already know works. There might be forms of life that work on completely different principles, using different solvents, different chemistries, different energy sources. But we can't search for those directly because we don't know what to look for. For life, as we know it, Enceladus checks boxes that no other place outside Earth does as completely. Let's go through them one by one. Liquid water? Yes. Enceladus has a subsurface ocean about 2% of the size of all of Earth's oceans. That's still an enormous amount of water, more than the combined volume of all 5 Great Lakes, and it's been liquid for potentially billions of years, heated continuously by tidal friction from Saturn's gravity. Energy source. Yes, hydrothermal vents on the seafloor produce molecular hydrogen through serpentinization. Chemical gradients exist between the warm, mineral-rich vent fluid and the cooler, open ocean water. Microorganisms called methanogens, microbes that live in extreme environments on Earth and produce methane by combining hydrogen and carbon dioxide, could theoretically feed on exactly this kind of energy gradient. Laboratory experiments proved that the methanogenic strain Methanothermococcus okinawensis can grow and reproduce under Enceladus-like physicochemical conditions. We have taken microbes from extreme environments on Earth, put them in conditions simulating Enceladus's ocean, and they survived. They didn't just survive, they metabolized. They produced methane. They did what life does, organic molecules. Yes, an expanding inventory of carbon-containing compounds confirmed to originate in the ocean, including the classes of molecules that are precursors to amino acids, lipids, and potentially nucleotides. The 6 essential elements, 5 confirmed: carbon, hydrogen, nitrogen, oxygen, phosphorus, all detected in the plumes. Sulfur likely present, but not yet confirmed. Stability over time? Yes. The tiger stripes have been erupting continuously since at least 1966. When Saturn's E-ring, which is formed by Enceladus's plume material, was first observed. The E-ring has been stable since its discovery in 1966, requiring year-on-year replenishment from Enceladus. That means this ocean has been in contact with rock and venting chemistry for at least 60 years of observation, and most likely for millions or even billions of years before that. Enceladus is thought to have an outer shell of ice covering a global ocean 20 miles deep, encasing a rocky core. A global ocean, 20 miles deep, sitting on top of a rocky core, with tidal heating from Saturn keeping the whole system warm and active, possibly for the entire history of the solar system. This is not a temporary unstable system. This is a permanent feature of a moon that has been around for 4.5 billion years. Now, let's compare Enceladus to its main competitors for the title of best life candidate in the solar system, because the comparison is instructive. Europa is Jupiter's moon and has long been considered the runner-up to Enceladus. Europa is larger than Enceladus, about the size of Earth's moon, and its ocean is thought to be much bigger, potentially containing more water than all of Earth's oceans combined. That's a lot of water. Europa also has evidence of tidal heating from Jupiter, and probably has a rocky seafloor in contact with its ocean, which means hydrothermal vents are plausible there too. But Europa has a problem. Its ice shell. Europa's icy crust is estimated to be somewhere between 10 and 30 kilometers thick, solid, hard ice. To access Europa's ocean, you'd need to land on the surface. Deploy a nuclear-powered cryobot that melts its way through kilometers of ice over a period of years, emerge into the ocean, and then somehow communicate scientific data back to a lander on the surface above. That is a staggering engineering challenge. NASA's Europa Clipper mission, launched in 2024, will study Europa from orbit and make flybys, but won't attempt to access the ocean directly. A full ocean access mission at Europa is a multi-decade prospect, likely not achievable before the 2060s or 2070s at the earliest. Enceladus's ocean is right there, erupting into space for free, waiting for a spacecraft to fly through it. Titan is the other major candidate. Saturn's largest moon has a thick nitrogen atmosphere, a complex organic chemistry, and lakes of liquid methane and ethane on its surface. Some researchers have speculated that life could exist in Titan's methane lakes. Not water-based life, but some entirely different biochemistry using liquid methane as its solvent. This is fascinating speculation. NASA's Dragonfly mission, currently in development, will land a rotorcraft on Titan in the early 2030s and explore its surface. But Titan's hypothetical life would be so alien. Using methane instead of water at temperatures around minus 180 degrees Celsius, that we might not even recognize it if we found it. Titan's astrobiology is real and interesting, but deeply uncertain. Enceladus, by contrast, has water-based chemistry that could, in principle, support life, very similar to what we know on Earth. The chemistry is familiar, the conditions are recognizable. The detection strategies are clear. We know what to look for. Then there's Mars. Mars gets a lot of press as the next place to look for life. And it's not wrong. Mars might have had life billions of years ago when it had a warm, wet surface. Some researchers think microbial life might still survive deep underground, where liquid water persists in brines or in aquifers. But Mars's surface is bathed in ultraviolet radiation. Its atmosphere is mostly carbon dioxide at very low pressure, and liquid water cannot exist on its surface today. Any life on Mars today would be deeply buried, hard to reach, and hard to detect. We've been studying Mars with landers, rovers and orbiters for 50 years and haven't found it yet. The contrast with Enceladus is stark. On Mars, life, if it exists, is hiding. On Enceladus, life, if it exists, might be spraying itself into space every second. Now let's step back and really think about what the 2025 discoveries mean in the context of the 20-year chain of discovery that preceded them. The chain goes like this. Point 2005. Jets discovered Enceladus is active. Something is happening under that ice 2006. The jets are confirmed to be the source of Saturn's E-ring. Enceladus is literally building one of Saturn's rings out of its own ocean water, 2014. Gravity measurements confirm a global ocean, not just a regional one. The whole moon has liquid water underneath, 2015. Silica nanoparticles found in Saturn's rings. They can only form when water at above 90 degrees Celsius reacts with rock. This is the first hard evidence of hydrothermal activity, point 2 Susan and 17, molecular hydrogen confirmed in the plumes, chemosynthetic energy available. Methanogens could survive here, point 2 Susan and 18. Complex organic molecules, macromolecular, up to thousands of atomic mass units found in the plumes. These are large, complicated carbon structures. The ocean isn't doing simple chemistry, it's doing complex chemistry, 2 Susan 23, phosphorus confirmed, 5 of 6 CHNOPS elements now detected. The ocean has the elemental inventory needed for life, 2025. New organic molecules confirmed as oceanic in origin. These include esters, alkenes, ethers, and nitrogen and oxygen-bearing compounds. The specific classes of molecules that on Earth lead to more complex, biologically relevant chemistry. This latest study is the culmination of nearly 2 decades of research built on Cassini's legacy. The chain of discovery began with the detection of jets in 2005, leading to confirmation of a global ocean in 2014, evidence of hydrothermal activity in 2017, the existence of organic material in 2018, and now the 2025 research has dramatically improved the case by confirming oceanic organic chemistry. Every single step in this chain moved in one direction. Not one discovery pulled us away from habitability. Not one finding said, actually, the conditions are less favorable than we thought. Every piece of new data was either neutral or made the case stronger. That's not how it usually goes in science. Usually when you investigate something carefully enough, you find complications. Things that seemed promising turn out to have problems. Hypotheses that looked clean get messy. That hasn't happened with Enceladus. 20 years of investigation, and it keeps getting better. There's something else worth understanding about why Enceladus is so uniquely scientifically accessible. And it has to do with contamination. One of the hardest problems in the search for life on other worlds is making sure that if you find something, it's actually from that world and not something you accidentally brought from Earth. Space agencies follow elaborate sterilization protocols for this exact reason. Spacecraft are built in clean rooms. Every surface is sterilized, but sterilization is never perfect. Some hardy spores can survive even the most aggressive cleaning protocols. And if you land on a potentially habitable world and introduce Earth organisms, and then your instruments detect life, did you find alien life? Or did you contaminate the environment and then find the contamination? This is called planetary protection, and it's taken extremely seriously. There are international treaties and scientific guidelines governing how we sterilize spacecraft, what level of contamination is acceptable for different categories of target, and how we handle samples brought back from other worlds. The Mars 2020 Perseverance rover, for example, was built to extremely strict cleanliness standards because Mars is considered a potential habitat for life. Enceladus's plumes are an extraordinary gift in this context. You don't have to land to sample the ocean. You fly through the plume. The plume comes to you. Your spacecraft never touches the ice surface. The only thing it contacts is material that was inside the ocean minutes ago and is now in space. the risk of contaminating the ocean itself is minimal, because you're not going into the ocean, you're collecting material that's already left it. This is one reason scientists have been pushing for a dedicated Enceladus mission for years. The science return per unit of engineering difficulty is essentially unmatched in the outer solar system. Cassini proved the concept. Fly through the plume, collect the material, analyze it. You're directly sampling an alien ocean without landing, without drilling, without any of the extraordinary challenges that a Europa or Mars subsurface mission would face. Now, Cassini was not designed for this. It was a Saturn system orbiter, optimized for studying Saturn and all its moons. Its instruments for analyzing the plume material were good, but not specifically designed to detect life. The cosmic dust analyzer that detected most of the organic molecules was primarily designed to study dust particles, not perform detailed organic chemistry. Its mass resolution was limited. It couldn't distinguish between left-handed and right-handed molecules. It couldn't detect cell membranes or nucleotides. What you'd want for an actual life detection mission is a suite of instruments designed specifically for the job. Mass spectrometers with much higher mass resolution and sensitivity. Instruments that can identify specific molecules at the parts per trillion level. Instruments that can distinguish between left-handed and right-handed amino acids. Because on Earth, life uses almost exclusively left-handed amino acids. And finding that asymmetry in an alien sample would be one of the strongest possible signatures of biological chemistry. If you find amino acids in Enceladus mix,
there are objects in the universe so immense and so powerful,
if they're almost entirely left,
they stretch the very limits of imagination.
cell membranes,
A place where gravity bends reality itself, where time slows and where light itself is trapped forever. This is not a star or a galaxy, but an infinite darkness wrapped in fire. A black hole so massive and powerful it dwarfs anything else we have ever found. And its name is...
the mission to Enceladus as one of the agency's top potential future projects. The proposed orbiter lander mission would launch around 2042 and arrive in the Saturn system in 2053. After arriving,
It lies near the border of the constellations Canis Venatici and Coma Berenices.
after sampling the plumes from orbit,
When astronomers at the Tenon-Sintla Observatory first recorded it in 1957, TON 618 appeared to be just another faint blue star. But later spectroscopic studies revealed its true nature. It was not a star at all, but the core of a distant galaxy powered by a black hole of unimaginable scale.
unlike prior missions,
TON 618 lies more than 18 billion light years away,
the L4 lander
so far that the light we see today began its journey when the universe was less than a quarter of its present age,
according to the US
at a time when galaxies were still forming. In the first generations of stars lit up the darkness. At such distance, TON 618 cannot be seen directly. It reveals itself through its glow, because this black hole is not an ordinary one. It is one of the most powerful phenomena in the universe. A quasar. Quasars are the blazing hearts of young galaxies, powered by supermassive black holes, consuming colossal amounts of matter. Gas and dust spiral inward, accelerated to nearly the speed of light. This accretion disk surrounding it radiates in every wavelength, from radio waves to visible light to deadly X-rays and gamma rays. Collisions and friction within the disk generate temperatures of tens of thousands of degrees. The result is a beacon so bright it outshines entire galaxies, making it visible across the entire universe. Within this maelstrom, magnetic fields coil and snap, launching colossal relativistic jets of plasma. These streams of plasma blast out from the black hole's poles at nearly the speed of light. Each jet stretches for millions of light years, longer than entire galaxies. They carry enough energy to shape their host galaxy itself, blowing away gas, halting star formation, and altering the course of galactic evolution.
Still selected as the #1 priority. The ESA team is working closely with the planetary.
TON 618 is one of the most luminous quasars ever discovered. Its energy output equals the combined light of 100 trillion suns. If it were placed at the center of the Milky Way, its bright light would outshine every star in our galaxy. It would be 23 times brighter than a full moon. And it would completely erase our night sky. Center of this radiance lies the true Colossus, a black hole with a mass of 66 billion suns. TON 618 is more than 16,000 times heavier than Sagittarius A, the black hole at the center of our own galaxy. Its event horizon, the point beyond which nothing can escape, is a sphere of darkness 400 billion kilometers across. Our solar system, from Mercury to Pluto, could vanish within it, with space left over.
Complex multicellular life requires much more stable, energy-rich environments to sustain it. Enceladus' ocean, while habitable, may not.
To stand near it would be to see the laws of physics bend before your eyes. Around the shadow of the event horizon, a glowing halo would form. It would be light being bent back toward the observer, trapped in orbit before finally plunging inward. Time itself would slow. Seconds near the horizon would stretch into years for the wider universe. An observer far away would see anyone close to the black hole frozen in place, trapped at the edge of eternity. At the last stable orbit, the black hole would dominate the sky. horizon of absolute darkness, encircled by fire. As we approach, colors would shift unnaturally. Radiation near the horizon would be gravitationally redshifted, stretched to longer, darker wavelengths. To our eyes, once bright light would fade into deep crimson, as if the black hole was bleeding the color from the universe itself. Further beyond lies only collapse, a singularity where density becomes infinite. And where our current understanding of physics breaks down completely.
Dissolved in the water. If methanogenic archaea or something...
Supermassive black holes are thought to begin as smaller cores,
they would feed on
the remnants of the very first stars,
reacted with dissolved carbon dioxide in the water,
or the direct collapse of massive clouds of primordial gas.
Extract energy from the process. The methane would dissolve
over billions of years, they consume everything around them,
and in some small fraction of cases,
swallowing stars, pulling in gas, and fusing with other black holes. But TON 618 pushes these theories to their limit. To have reached 66 billion suns so early in cosmic history, it must have grown at an extraordinary pace. Its scale suggests either an unusually massive origin or feeding conditions in the young universe far more extreme than we once believed. Its very existence challenges our understanding of how black holes evolve. Quasars like TON 618 are not just monsters, they are also windows into the past. Because they shine so brightly, their light travels across billions of years, passing through the gas that fills intergalactic space. By analyzing this light, astronomers can measure the chemistry of the early universe. They can trace the distribution of matter and study how galaxies grew and changed in the first billion years after the Big Bang. TON 618 is both destroyer and guide, illuminating the hidden structures of the universe. And when we look upon it, across 10 billion years of distance, we glimpse both the terror and the wonder of the cosmos.
Philosophers have a term. It's called the anthropic selection effect. We can only observe the universe from a place that produced observers. Earth produced us. So of course we observe that Earth has life. But that doesn't tell us how common Earth-like conditions are, or how likely life is to arise when those conditions exist. It's a sample of one, and you can't do statistics with a sample of one. If we find life on Enceladus, microbial, simple, utterly different from anything on Earth in its evolutionary history, everything changes. You now have two independent data points. Life arose in two completely different environments in one solar system. That is not a coincidence. That means life is not a miracle. It means that wherever the right conditions exist, life tends to appear. It means the universe is probably full of it. The implications cascade outward. If life arose independently in two places in our solar system, then of the roughly 100 billion star systems in the Milky Way alone, and the countless ocean worlds circling those stars, life has probably arisen in enormous numbers. Not intelligent life necessarily, not technological civilization, but life, biology, the chemistry of self-replication and metabolism arising wherever conditions permit. That would be one of the most transformative scientific discoveries in human history, not just in space science, in all of science, in all of human thought. It would also trigger immediate, urgent questions. If life exists on Enceladus and on Earth, did it arise independently, or could there be a connection? Could material have been exchanged between the inner and outer solar system, carrying microbes between worlds? Panspermia, the idea that life can be transferred between planetary bodies, is speculative but not impossible. Impact events can blast material off surfaces at escape velocity. Some of that material can eventually cross the solar system. Some fraction could survive the journey if shielded from radiation inside a rock. The question of whether life on Enceladus and life on Earth are related or independent would be the most important scientific question of the next century. And the answer would come from chemistry. If Enceladus's life uses the same amino acids, the same genetic code, the same molecular machinery as Earth life, that suggests common ancestry or transfer. If the biochemistry is completely different, different amino acids, different chirality, different molecular architecture, that proves independent origin and establishes life as a universal phenomenon, the reverse is also worth thinking about. What if we go to Enceladus, fly through those plumes, collect that ocean snow, run it through the best instruments we can build, and find nothing? What if the chemistry is rich and complex, but entirely abiological? What if life, even in this seemingly ideal environment, simply did not arise? That would also be a profound discovery. It would tell us that the emergence of life is not automatic, even given the right conditions. That there is some additional step, some additional ingredient or event or process that is required, and that this step is rare. That life on Earth may truly be extraordinary, possibly unique. Some researchers call this the hard step hypothesis. The idea that at some point in the origin of life, there was one particular transition that was extraordinarily unlikely, a kind of molecular lottery that had to be won before anything could proceed. If that step is genuinely rare, then even with trillions of suitable environments across the galaxy, actual life might be exceedingly rare. Maybe Enceladus got all the way to the starting line and just never had its lottery ticket called either answer, life found, or no life found, would be transformative. The universe would look different after either result, but given everything we know right now, given the richness of the organic chemistry, the confirmation of hydrothermal vents, the phosphorus, the 5 of 6 CH-NOx elements, the methane anomaly, the fact that Earth organisms can survive in simulated Enceladus conditions. The probability that something is happening in that ocean is not small. See, scientists are careful not to put a number on it publicly, but ask them privately, and many will say they'd be genuinely surprised if nothing was there. Now let's think about the scale of what we've been talking about physically, because I think it helps to really picture where this ocean is. Enceladus is about 4% the size of Earth, at just 505 kilometers across. If you put it in the middle of the continental United States, it wouldn't stretch from coast to coast. It would comfortably fit inside a single large state. It's tiny. And yet, this tiny moon has a global ocean. The water ocean on Enceladus is about 10 kilometers deep and lies beneath an ice shell about 30 to 40 kilometers thick, 10 kilometers deep. The Mariana Trench on Earth, the deepest point in any of Earth's oceans, is about 11 kilometers deep. So Enceladus's ocean is comparable in depth to the deepest abyss on Earth, but global in extent. It wraps all the way around the Moon, above it 30 to 40 kilometers of ice. Below it, a rocky core being squeezed and heated by Saturn's gravity, producing hydrothermal vents on the ocean floor. And this ocean has been sitting there, warm and chemically active, for potentially billions of years. Not thousands of years. Not millions, billions. The same duration as the history of life on Earth. On Earth, we think life appeared within the first billion years of the planet's formation, possibly within the first few 100 million years. The earliest evidence of life on Earth dates to about 3.5 billion years ago, and some researchers argue for signs of life going back 4 billion years or more. That means life appeared on Earth within about 600 million years of the planet forming. Enceladus's ocean is at least 4 billion years old. If the same time scales apply, if life arises within the first billion years, whenever the right conditions are present, then there has been plenty of time, more than enough time. The counter-argument is that Enceladus's ocean might not have been continuously habitable. There are open questions about whether the tidal heating has always been at the current level, or whether it has varied over time. If there were periods when the ocean partially or fully froze, that would have disrupted any life that had appeared. But the evidence from the geology, the very young surface in the South Polar region, the ongoing plume activity, suggests that the system has been active for a very long time. And even if there were freeze-thaw cycles, that doesn't necessarily kill everything. Some of Earth's most resilient extremophiles can survive being frozen solid for extended periods and then revive when conditions improve. Tardigrades, microscopic animals, sometimes called water bears, can survive being frozen, desiccated, exposed to radiation and even the vacuum of space. Certain bacteria can survive in permafrost for millions of years. Life, once established, is remarkably tenacious. Now let's think about what a day on Enceladus might look like if you were somehow there. Not because we'll ever send humans, but because picturing it helps make the science feel real. You'd be standing on one of the most pristine and hostile surfaces in the solar system. The sky above you would be pitch black, but not empty. Saturn would hang enormous in that sky, about 60 times the apparent size of our moon from Earth's surface. Its rings would be visible as a brilliant arc across the sky. The light would be dim. Sunlight at Saturn is only about 1% as intense as sunlight at Earth, but enough to faintly illuminate the landscape. The surface temperature would be around -200 Celsius. Your suit would need extraordinary insulation. The gravity would be almost nothing. Enceladus's surface gravity is less than 1% of Earth's, so every step would be an enormous slow-motion leap. The landscape around the South Pole would be extraordinary. Ridges of ice pushed up on either side of the tiger-striped canyons. Boulders of ice, the size of houses, scattered across the surface, deposited by previous eruptions. A fine mist of water ice particles constantly falling from the plume above, the snow from the ocean below drifting down in the dim Saturnian light. And beneath your feet, 30 kilometers down through solid ice, a dark ocean of salt water, warm from the rocks below, churning with chemistry that might, just might, be alive. That is not a metaphor. That is the actual reality of a place that exists right now, 1.3 billion kilometers from Earth. Now let's return to the Earth connection one more time, because it's the emotional heart of why this matters to every person alive today. We are, in a profound sense, made of this stuff. The atoms in your body were forged in ancient stars. The carbon in your DNA was produced in stellar nucleosynthesis, in stars that exploded before our solar system formed. The water in your cells has been recycled through geological processes for billions of years. The organic chemistry that underlies your biology is the same kind of organic chemistry we're finding in Enceladus's plumes. We are not separate from the universe. We are an expression of it. The question of whether life exists on Enceladus is not just an astronomy question. It's a question about whether what happened here, the emergence of chemistry that copies itself, that metabolizes, that evolves, is a unique accident or a universal tendency. It's a question about whether the universe tends toward life, or whether life is a cosmic exception. There is a reason why every major space agency in the world considers the search for life one of its central scientific missions. It's not because of the commercial value. It's not because of national prestige. It's because this question, are we alone, is the deepest question that human beings can ask about their place in the cosmos. It has been asked by philosophers and theologians and scientists for centuries. Now, for the first time, we have the technology to begin answering it, not theorizing, not speculating, actually going there, actually flying through that ocean, actually running the test. And Enceladus might give us that answer within the lifetime of people alive today. The mission launches around 2042. It arrives at Saturn around 2053. It lands on Enceladus around 2058. The lander will operate on the surface for 2 to 4 weeks, collecting samples and running them through instruments designed specifically to detect the signatures of life. If the data comes back positive, if the instruments detect amino acids with asymmetric chirality or cell-like structures or metabolic products or any of the other specific signatures of biology, then sometime around 2060, humanity will know, we will know that we are not alone, that life is not an accident confined to one small planet in one ordinary solar system, that the universe is, in some meaningful sense, alive. That moment, the moment of confirmation, the moment when the data comes back and the team in the control room goes quiet and then erupts, will be the most important moment in the history of science. More important than Copernicus realizing Earth goes around the sun, more important than Darwin realizing species evolve, more important than Einstein realizing space and time are relative, because all of those discoveries were about how the universe works. This one would be about whether the universe lives. Think about what follows from that. Every religion on Earth would be forced to re-examine its assumptions. Every philosophy of mind would be challenged by the question of what kind of consciousness, if any, might emerge from a completely different evolutionary lineage. Every government on Earth would have to decide how to respond to the knowledge that life is not rare, that the galaxy is inhabited, that somewhere out there evolution has been running its experiments independently for billions of years, even if it's just microbes, even if it's just methanogens living in the dark around a hydrothermal vent on a moon orbiting Saturn. The implications are enormous. The first word of that discovery would travel around the world in seconds. Every person alive on that day would remember where they were when they heard it. And even if the result comes back negative, if the lander sits on the ice of Enceladus and the instruments find beautiful chemistry, but no biology, that result is still historic. We will have answered the question. We will know. We will have made the most careful, thorough, well-equipped measurement. Science can make, and we will have an answer. And science can build on an answer, even a negative one. Everything we've covered in this video, the discovery of the jets in 2005, the chain of revelations about water, vents, organics, phosphorus, the 2025 confirmation of new organic compounds directly from the ocean, the ESA mission now officially in development. All of it is the prelude to that moment. Every step has been building toward the day. A spacecraft sits on the south pole of a tiny, impossibly distant moon and runs the most consequential chemical test in human history. The tiger stripes are waiting. The ocean is already venting. The plumes are already in space. Enceladus has been doing this for billions of years, completely indifferent to whether anyone noticed. We noticed, and we're coming back. For the video that goes perfectly with this one, go watch the one on Europa that's up next on your screen, because Jupiter's ocean moon has secrets of its own.